Welcome to this explainer. Look, today we're going to completely shift how we think about network ports. We are moving away from abstract, vague concepts and stepping right into a precise, technical framework. If you've ever wondered how your computer juggles dozens of applications online without breaking a sweat, you are definitely in the right place.
All right, here's our game plan for today. We'll be looking at the multiplexing problem, 16-bit unsigned integers, the 4-tuple socket connection, TCP segments versus UDP datagrams, IANA port categories, and finally, those essential protocol specifications. Let's get right into it.
Section 1. The multiplexing problem. To really get this, we first have to understand the fundamental challenge that makes ports absolutely necessary in the first place. Think about it like this. If a delivery driver has a building address, right, but no apartment numbers, they literally can't deliver the packages. They know the building, but they have absolutely no idea who gets what. This perfectly mirrors how an IP address works on a network. The IP address alone identifies the machine, sure, but it cannot pinpoint the correct receiving application running on that machine. I mean, how does the incoming data know if it's supposed to go to your web browser, your email client, or an FTP server?
Well, ports are the answer. They step in and solve this issue by providing what's called a multiplexing service. Basically, multiplexing allows an operating system to take a single IP address and slice it up into distinct, totally separate data streams for different processes. By tagging each application with a specific port number, the operating system can flawlessly route incoming traffic right to its exact intended destination. No crossed wires, no mixed-up data.
Moving on to Section 2. 16-bit unsigned integers. Let's look at the actual mathematical boundaries placed on these logical endpoints.
You know, in computer networking, ports aren't just arbitrary labels pulled out of thin air. They are defined mathematically as 16-bit unsigned integers. Because of this specific, hard-coded architectural choice at the transport layer, a system can only have port numbers ranging exactly from 0 to 65,535. That's the hard limit. Now, port 0 is generally reserved. You won't use it for standard applications, which leaves a finite, mathematically strict pool of endpoints for literally every single piece of software trying to communicate over the internet.
Okay, Section 3, the 4-tuple socket connection. Let's jump into the exact mechanical formula for how these numbers actually establish network communication.
An internet socket is really the absolute backbone of a connection. A socket is created when an application binds its input or output channels to a specific transport protocol, a network IP address, and a port number. It acts as a unique file descriptor for the operating system. You can basically picture a socket as a fully realized doorway that data passes through to either leave or enter a machine.
So here's the crucial part. How does a busy server differentiate multiple users connecting at the exact same time? It tracks a precise 4-tuple connection formula. Imagine thousands of users hitting a single web server on port 80 simultaneously. Why doesn't the server just crash and burn from confusion? It's because every single connection is defined by 4 strict variables: the source IP, the source port, the destination IP, and the destination port. Even if the destination IP and port are completely identical for everyone, the client's unique source IP and dynamically generated source port guarantee that every single data stream stays totally distinct.
All right, Section 4. TCP segments versus UDP datagrams. Next, we really need to contrast how transport layer protocols use these sockets differently to move data.
Because as we know, not all data travels the same way. The Transmission Control Protocol, or TCP, is kind of like sending a certified letter. It relies on protocol data units called segments. TCP establishes a really strict connection. It verifies that the data arrived in the perfect order, and if packets are lost, it asks for them to be resent. Highly reliable for sure, but that comes with a lot of overhead. On the flip side, the User Datagram Protocol, or UDP, utilizes datagrams to rapidly blast data out there without verifying a single thing. It's like an announcement over a PA system. The data goes out instantly, but UDP honestly doesn't care if you actually heard it.
Actually, there's a quote from a network engineering forum that I just love. It goes, "I like telling UDP jokes because I don't care if you don't get them." It's a brilliant joke, and it perfectly nails the stateless, unconfirmed engineering logic behind UDP. It is designed purely for speed. If you're watching a live video stream or playing a fast-paced multiplayer game, you would much rather drop a pixel or a frame than wait for the entire network to halt, find the missing data, and send it all over again.
Which brings us to Section 5, IANA port categories. Let's see how the Internet Assigned Numbers Authority manages and organizes all 65,535 of these endpoints.
Look, to keep the whole internet from just devolving into total chaos, the IANA divides ports into 3 highly rigorous categories. First, at the lowest tier, we have ports 0 through 1023. These are the well-known ports. They are restricted to core system processes and usually require strict administrative privileges to even bind to. Then, the middle tier, running from 1024 to 49151, are the registered ports. These are assigned to specific applications like databases or various open-source tools. And finally, the highest tier, from 49152 all the way up to 65535, are the dynamic or private ports. These are the ephemeral, temporary ports that your client browser grabs just for the duration of a single session and then tosses back into the pool when it's done.
Section 6. Essential Protocol Specifications. For our final section, we're going to map out the technical specs for the most critical application protocols you'll encounter out in the wild.
When we map out a broad architectural overview, it's fascinating to see how specific application protocols are permanently anchored to these well-known and registered ports. I mean, when devices communicate, they absolutely must speak the same language, the protocol, and they fully expect to find that specific language being spoken at a very specific port number.
Let's run through the absolute essentials here. Standard unencrypted web traffic relies on HTTP using port 80, while encrypted secure web traffic uses HTTPS on TCP port 443. Now, if you need a secure shell login to a remote server, you're going to use SSH on TCP port 22. The Domain Name System, or DNS, which translates those website names into IP addresses, uses port 53. And what's cool about DNS is it uniquely leverages both TCP and UDP depending on the specific task. Finally, DHCP, the service that dynamically assigns IP addresses when you join a network, relies entirely on UDP, using port 67 for the server side and port 68 for the client.
So, we've covered the mechanical genius of multiplexing, the strict math of 16-bit integers, and the core protocols that literally run our modern world. But before we wrap up this explainer, I want to leave you with something to chew on. As our network infrastructure rapidly evolves, especially with the total depletion of IPv4 addresses and the massive ongoing transition to IPv6, we really have to ask ourselves, how will these foundational numbering systems adapt to the future of the internet? Will a 16-bit structure always be enough for us? It's definitely something to think about. Thanks so much for joining me for this explainer.